Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 39, we will cover support vector machine. The different concepts that we will cover will be the basics on support vector machine. Then we will talk about hyperplane, margins and support vectors, which are fundamentals to support vector machine. We will talk about its mathematical formulation, particularly in the linear form. And then we will talk about both hard and soft margin SVMs. We will talk about nonlinear SVMs and how we go around it using the kernel trick. Then we will talk about some common kernels, some different pros and cons of SVM applications. We will then take an example of the residential mobility model, which we discussed earlier, and then we will develop Python code for SVM for this particular model. And then finally, we will compare the model results with other algorithms and see which one performs in what way. So, support vector machine is a supervised learning algorithm, and in most cases it is used for classification, but sometimes we can also use it for regression as well. And what classification means is basically it's a geometrical problem, and we need to separate points in a feature space. Now, this space could be 2D, 3D, or even a hyperplane as well. Or a higher dimensional context as well. So, this could be accordingly. We would like, in case of a 2D, we will like to choose a line. In case of a 3D, we can choose a plane, or in case of higher dimensional data, we can go for a hyperplane. So that means the classification could be a line or could be some sort of a plane as well. Now, the job of SVM is to find the optimal hyperplane. That means out of any infinite possible hyperplanes, SVM will choose the best possible decision boundary. Now, we have already learned decision trees, logistic regression, k-nearest neighbors. So, these are the other algorithms which we have used for doing classification tasks. Now, in case of decision trees, what we did was we partitioned the data in a sequential manner. That means we created these if-else, elif rules, and based on that we were able to classify a group of data into different classes, or we could even do regression. Now, this kind of algorithms, decision trees are more transparent, easy to understand. We can explain the logic of our decisions, and it could be used for conveying the idea to different stakeholders, and we can frame different rules out of that. Now, in case of logistic regression, what we found was that not only we can partition, but it is a probabilistic linear parametric model. So we are fundamentally assuming linear relationship between the predictors and the target, but it's a probabilistic model, and that's the beauty of it. And class probabilities, obviously, we once we have a linear model, there is a score that comes out of it, and we already discussed this earlier, and we can convert it into probability using the log odds of that particular linear relationship. Now, the beauty of this is we can predict the probability of a choice, and also it is very, very interpretable. That means we know the coefficient strengths, we know its direction, and it is used for determining which is important, which is not, and we could understand the sensitivity of different policies that we will undertake, and we can draw different statistical inferences from this particular model. So that's the beauty of a logistic regression model. And then we also learned about k-nearest neighbors models, which we said that it could be made into a baseline model, and it deals with small data sets when there is not too much data available, and it usually looks into local context. That means local data matters, right? So it's a local instance-based method that predicts outcomes using similarity among near observations in feature space. So that means whatever are the near observations, accordingly I will classify the current observation. So these are the, all of them has got the pros and cons, but how support vector machines goes above them, or rather, gives a alternative approach for classification is, it's a global margin-based classifier. Now, global basically means we end up doing a global optimization. So that means there is only a single solution. And then margin-based classifier means that obviously there is a gap, we try to create a gap between the different classes, and we make sure that the classes are properly segregated. So at that, and it finds an optimal decision boundary using convex optimization and kernel methods. Now kernel methods we will learn, that means in higher dimensional data sometimes it's difficult to segregate or find a plane. So we use a trick called kernel trick, so that using that we can try to identify which should be the margin or how we can determine that particular margin, right? So the accuracy is pretty good in this support vector machines, and usually this classification accuracy is critical for very complex nonlinear problems, and that is where support vector machine shines. So that means in case of very complex problems, we will go for support vector machines. So over here we will show you the concept of hyperplane margins in support vectors. So I have a 2D space. These are two features, x1 and x2, and then these are the different points belonging to and we need to find out that okay, each point has got an x1 and x2 value, and we need to find out that which forms which class. Of course, there are two classes. One is this circle of red color and this squares of blue color. How do I separate them? So if you see the distribution of these particular points, we see that there is a gap between this, and we can draw the right line or the decision boundary in between, like shown over here, and then we can say that this actually divides these two classes. Now what happens is, now along with that, what we can do is we can introduce the concept of margin. Now margin is the distance between the decision boundary and the nearest data points. That means this is the decision boundary, and this nearest data points of this class is over here, and nearest data points of this particular round class is over here. So obviously this margin is the distance between them. So if we want to increase the margin, that's our goal. So in case of SVM, our goal is to increase this margin as much as possible, and the more is the size of the margin, more robust is the classification. So SVM chooses the hyperplane that maximizes the margin. Larger margin is lower uncertainty, and lower uncertainty means lower mixing of different classes, and it keeps the boundary as far away as possible from both classes. And larger the margin model, larger is the margin, the model is more robust, or more, it can generalize more. And many hyperplanes can separate the classes if data is linearly separable, and 2D line, 3D plane, higher dimensional hyperplane, and SVM will search for the best separating line in this particular situation. Now along with this, there is the remaining is what are support vectors then. Now support vectors are the data points closest to the decision boundary. So that means these are the support vectors. Now as you can understand that the distance between the decision boundary or between the margins is based on the support vectors, right? So support vectors are the data points closest to the decision boundary, and only the support vectors matters. That means the position of the hyperplane or the classifier that we will develop depends on the position of this points which are nearest, and these are the support vectors. So SVM solution will not change when the faraway points or even there are outliers, those actually change, and that means those are far from the decision boundary, and that has got no impact on the location of this particular separating hyperplane. Now to convert it into a linear form, over here you can see the decision function of the classifier is basically a line where this fx is the function, and then w is the feature vector of one observation, and then x is the feature vector of one observation, and we can have x1, x2 depending on how many vectors are there. And then w is the weight of each of these vectors, which is also the feature importance, as you can say, and b is the bias or intercept. Now the role of bias or intercept is it can shift the decision boundary to either left, right, up or down. So what happens is we get a score from this particular equation, and we can have w1, x1, w2, x2, and that is what is we have used t for that. And then fx, when the total score fx is greater than 0, the points belongs to class 1, or if it is lesser than 0, the point belongs to class -1. So that is how we classify between the different classes. Now our goal is to optimize the which is in hard form, that is if we have a hard margin, that means we have a fixed margin, to minimize this value of w, and we take half as well of that, and then we take a square of that. Now this w basically represents the length of the vector. It's the length of vector w. So this, this sign actually says it means the length of vector w. Now what is w? W basically, if we have got two variables, two features x1 and x2, and we have got w1 and w2. So w actually represents this w1 by w2. So it is like a a combination of both these particular weightages of these vectors of these particular features. So this actually is this, again, it's the sort of a slope. Depending on how different these two are, that particular slope will vary. So w controls how steep the boundary is, and it determines this particular, over here if you see, if we have x1 or x2 in this particular in two direction, this if in case of a small value of w, then we get a flatter we get a flatter slope. In case of a higher value of w, we get a longer slope, right? We have a steeper slope. So w controls how steep the boundary is, and that if the boundary is steeper, that means in that case the margin would be narrower. If the boundary is flatter, that means if w indicates a flatter boundary, then the margin would be wider. So our goal is to maximize w square, because we want a higher margin, right? So minimizing w automatically maximizes the margin, and that is the goal of SVM. Now subject to a constraint, and that is given over here, wi into this w t xi plus b greater than equal to 1, which ensures that from the decision boundary, the margin should be at least 1 unit away. So that is what this constraint ensures. So the constraint ensures that every training point is correctly classified and lies at least 1 unit away from the decision boundary, thereby enforcing a minimum margin. Now hard margin SVM is used only when data is perfectly linearly separable. So that is, we will use this when data is perfectly separable. That is, there exists a straight line or hyperplane that separates the classes without any errors. Now, but problem is, real data is much more chaotic. There are measurement errors, there are overlapping class boundaries, then there is noisy data, incorrect or noisy labels we have wrongly classified. So that means this kind of perfect separation is unrealistic. That means we cannot say that hard margin we can assume, but in most cases we cannot use a hard margin. So what we do over there is we use a soft margin. So you can see in this image over here, in this case, the data is perfectly separated. We can draw a hard margin. Actually, the margin, if let us assume there are some triangles over here as well, and then there are some circles over here as well. So that's why this is the margin that is being drawn. But in most cases, data is not like this. Data is actually a little bit more chaotic. There is overlaps, there is mixing. So in this case, we go for something called a soft margin. Now, soft margin SVM is an extension of hard margin SVM that allows some training points to violate the margin or be misclassified in order to handle noisy overlapping real world data. Now, how do I handle that? So what I do is I introduce a slag variable psi, and which is greater than 0, of course. And then if psi is equal to 0, then basically it means everything is correctly classified outside the margin. That means every point is outside the margin. But if it is not, that is, if it is something between 0 to 1, because we already remember that the last constraint said that the margin has to be at least 1 unit away. So if it is 0 to 1, that means it is inside the margin but in the correct side. And if it is greater than equal to 1, that means it is misclassified. That means it is in the other domain, other side. So the optimization problem changes a bit. That means in case of short margin, we introduce, this minimum half of this w square, this remains same. We introduce this additional term. So that means C multiplied by summation of all the different size or the slacks that we add for each of these points. So what we do is this part, this C, summation of size, it helps us to penalize the classification error. Our goal is to maximize margin, right? but we have to find the right balance between maximizing margin and increasing the number of errors. So obviously, if you can see that if I try to increase the margin further, obviously the number of errors would be more. So I have to find the right balance between the number, that how much the margin should be wider and how many misclassifications I will allow, or what kind of errors I should allow. So in this case, to find the right balance, the C parameter is utilized, and for large C, we penalize errors strong. That means we introduce a penalizing terms. That means if C value is larger, that means we penalize error strongly, and it results in strict classification, and it results in a smaller margin. But if it's a smaller margin, then there is risk of overfitting or otherwise low bias and high variance, right? So that means the bigger margin is ideal because there is more generalization, less overfitting. And but in case I do that, then what happens? The classification problems increases. That means more values would be on the other side. So I have to find the right balance, right? So C actually determines how to control this, dilemma. And then in case of small c, this allows more violations, which results in larger margins. But this of course results in better generalization, which is high bias and low variance. So we have to, by tuning the value of C, I can use different values of C to find out which gives us the right prediction or what would be the right accuracy scores, and accordingly we can go forward. Now coming to more complex data sets, or where we cannot fit a linear line. That means if many data sets are not linearly separable, and that means we have to go for curved or complex boundaries. So that we are going into the domain of nonlinear SVM, right? So usually data sets like behavioral data and all are usually nonlinear in nature, right? We can assume some amount of linearity, but in many cases those are nonlinear. So this requires nonlinear decision boundaries. Now, if the decision boundary is nonlinear, can we still use the concept that we used earlier? That is, can the concept of margins be still used? Because it was based on the concept of it's a plane which equally distant, or it's a straight line in that way. So what we do is, we, instead of changing the algorithm, that means the decision boundary remains same, the way we look at the data or the points, we actually change that, right? So that means instead of having points all across a different space like this, if I change the surface where these are projected and makes them come closer together, in that way we can say that we are changing the way the data would be projected, but the actual actually it is not that. That means we are not going to calculate the actual distances after converting them. So that is the concept what we are going to use in the kernel tree. So instead of changing the algorithm, we change the feature space, and to do that we have to use the kernel trick. So what it means is we map the data into a higher dimensional space, but that means we have to compute the value of phi x. For that we need to define a kernel function. That means how a particular point is going to be changed in this higher dimensional space. But calculating this is very difficult, right? So instead of explicitly computing this particular value, where exactly this point is located, and then finding the distance between the points, what we do is we take the dot product of kernel xi xj for these 2 points. We take the dot product between the transform points, that is over here. So this is the dot product phi xit into phi xj, and then this phi x actually represents the point in the higher dimensional feature space, but as soon as I take the dot product, it becomes a measure of similarity between the 2 vectors. So instead of using the concept of margin, what we now use is, that means in case we are converting the data into this higher dimensional space, what we look forward is for similarity, that is similarity between the vectors, between 2 vectors of the existing data and whatever we are trying to classify. So the decision boundary depends on pairwise similarities, because this dot product is nothing but a measure of similarity. So pairwise similarity in kernel SVM, the model does not think in terms of raw coordinates x1 and x2. Instead, it thinks in terms of how similar is this point to other points, right? So the question that we are asking is how a new point that is being classified is similar to the other points, and this similarity is computed using this kernel function, or which is this dot product. So that's the concept we are using. So if we have a class A and B, and it's a had in a very non-linearly it is divided, what we do is we use a kernel function to actually change the data, and it looks like this, where I have a better chance of classifying by putting a plane which separates these two groups of data points, right? So but once we do that, the point is becomes very difficult to compute the distances and then create a plane in between. So instead we find the similarity between which needs to be predicted and the existing points, and that is how we will go for this kernel trick avoids us to do detailed computations and still classify these data points. So we use different kernels, and there are several kernels that are used, like linear kernels. It is best suited for high dimensional sparse data such as text features or indicator variables. And then there is polynomial kernel, which captures feature interactions with moderate complexity by modeling non-linear relationships explicitly. And then there is the most popular one, which is the RBF or Gaussian kernel. It is what it does is it models local similarity and creates highly flexible nonlinear decision boundaries. And then we also have sigmoid kernel, which is based on mimics the network activation behavior, neural network activation behavior. We will learn neural networks later. And but there is difficulty in using this because of there is some amount of instability, some tuning, hyperparameter tuning difficulties, and so on. So mostly we will use the RBF or Gaussian kernel. Now this as we discussed, it measures the similarity and based on the distance between the data points, and it assigns higher similarity to closer points and lower similarity to distance points. So this is the kernel function that you are seeing. So we take an exponential of minus gamma, and then we take this into xi minus xj. This is the distance between these 2 points, and we will take this particular kernel function, and that is how the data points get transposed. And each data point acts like a center of influence, with influence decreasing smoothly with distance. That's why this gamma factor is introduced. So we try to say that, okay, what is if I change the value of gamma, then I can make sure how sensitive it is, right? So the decision boundary is found by combining these local influences, and gamma controls how far the influence of a single training point reaches, right? So if the gamma value is small, that means the influence of that point is wide. That is, it's sort of you can say a weight, and it's smooth global decision. It results in a smooth global decision boundary, and so that's higher bias and lower variance. And if the influence is local, in case of large gamma, then it's highly carved and complex boundary, lowers bias and higher variance. So what we do is, in case of this SVM, where we are using this RBF or other kernels, then what we can do is we can change the gamma value, if it is a RBF or polynomial kernel. In other cases, we can change C as well as we can choose which kernel. That means this is how we tune the hyperparameters. First, we can give a choice between linear, polynomial, or RBF, and see which one is performing well. And if it is RBF, we can further tune the gamma as well. And then also we can change C, which we have already learnt earlier, where we are talking about this soft classification and all. So talking about SVM applications, SVM optimization is convex and quadratic, which ensures a single global optimum. That means there is a single solution for both hard and soft margin formulations. So that's why classification accuracy is very high. And we can also use SVM for multi-class SVM as well. In general, SVM is basically binary, but we can go for multi-class as well. But the approach there is one versus the rest, or one versus one. So we can do pairwise comparison, and then we can summarize that, or we can take one versus rest, and we can summarize the results to see what would be the the more voted class, or so on. Then support vector machines have a strong theoretical foundation, offer excellent generalization, and perform well in high dimensional feature spaces. That is, where we are going to use it. These are robust to overfitting with proper tuning and rely only on subset of critical training points called support vectors. So we don't require all, only a few points would be utilized. And SVM is sensitive to feature scaling, requires kernel and parameter tuning that we just learned, and it is computationally expensive for large data sets. And that means for very large data sets we can avoid SVM, and compared to regression it is much less interpretable, right? So we cannot say that which features are influencing how much and so on. But SVM is well suited for small and medium data sets with complex or nonlinear class boundaries where prediction accuracy is prioritized over interpretability. So this is where, in which cases we are going to use SVM. So coming to the residential mobility model, just to remind you that we had a decision variable which says that a group of households in a particular city during a particular planning period or a time period, are they going to move or not? That means, are these households planning to change their house within this planning period, right? So the decision to move is 0, and the willingness to move is, if they are saying that yeah they are willing to move, that we are taking as 1, right? So what are the predictor variables? We have taken many predictor variables, like what is the income of that family. Of course, that has a role to on a decision for a family to move, and it is categorical LIG, MIG, HIG 1, 2, 3. Then number of members, which is a count or a continuous variable, so it's numeric, and that means the more the number of members, most likely is the chance to move. And then similarly, marital status, age of the head of the household, education level, occupation level, family type, if a child is present or not, how many workers of there is in the family, what kind of housing they are right now staying, what is their ownership, are they staying in rental or owned accommodation? Because if it is owned, there is less chance to move. If it is rental, there is more chance to move, right? Then are they local people or they have migrated to this area? Then how many cars they own, what is the number of persons per room, that is, what is the density of occupancy for this particular household. And that actually, if it is high, then obviously they want more rooms, that means they want a more building, they want to move out. And similarly, the neighborhood characteristics, what kind of amenities are present, all these things are also there. So we import pandas as PD, numpy as NP, then SV. These are the standard things that we have already done earlier. So we importing trained test split, stratified k-fold, then we can also do something called grid search. We will explain that. And then we are taking the column transformer, we are having the pipeline, we are using one-hot encoder to encode the categorical variables, standard scaler to normalize the numeric variables. Then simple imputer is there to impute, that is, in case of empty fields or empty cells, we can impute that with either median or some other values. And then we are importing SVC, support vector machine. We are also importing the accuracy score, confusion matrix, classification report, and ROC AUC score. Now first we load the data set. Target variable is decision to move, and so everything else is dropped, and that after we drop this decision to move the target variable, then remaining columns are the ones which are using as features. So that is happening here. Now what I am doing is, so once we are finalizing x and y, then we are determining which are categorical variables and which are numeric variables. So that is listed over here. So we, based on our knowledge, we say that, or based on the data set, we can enter this data. That is this monthly income, marital status, education, occupation. These are all categorical variables that we are using. And similarly, these are the numeric variables that we have taken. Some of these are not exactly numeric, these are rating scales, but in 1 to 5, but for the sake of simplicity, we have assumed 1 to 5 is linear. That it's not like the gaps between each of this rating is same. So when I can then I can do some checks, like if some variables are missing after I add up all categorical and numeric, is it equal to the columns that has been entered in features? If not, we can raise a error and we can print whatever it requires for that. So first we are printing the numeric and categorical variables, and that is over here. And once we have done that, we can start building the model. So first we call the xtrain, the train test split function, when we store the values of xtrain, xtest, ytrain, ytest. So that means we are dividing the data set into two parts for the training and for testing, and we are using a division of 0.3. That means 70% and 30% would be the division between train and test. Random state is 42 to replicate the same split, and stratify y make sure that the train and test has got equal numbers of yes and no's. And then we formulate our pipelines. The first pipeline is, we impute for numeric variables, we impute median, to fill it up, those particular cells, and then we introduce standard scaler to scale it. Whereas for categorical variables, we impute it by the most frequent, and then we also use one-hot encoders to encode it. Then we have the transformers. Using transformers, we can actually call this, we can create the pre-process step where we are calling, this numeric, these two particular, steps, so that we can convert into a numeric variable. We are scaling the numeric variables, and we are scaling as well as imputing the numeric variables, and also scaling and imputing the categorical variables. So we are calling the numeric pipe and the categorical pipe, which we have defined here. And then what we do, then of course we have to do the pipeline, where one part is to add the pre-processing part, and the other is the model part, right? And SBC is called here, probability is true, class weight is balanced, and random state is 42. And because probability is given true, that means we enable probability estimation, not just classification, and it can also handle class imbalance as well. That means that class weight is balanced, means we can divide the class properly. So that means we could have done it in one step, but here we are creating two steps, combining them in pre-process, and then again we are creating a pipe with both pre-process as well as the model formulation, which comes from over as both of them together. So now what we do is we create something new, that is, we are first specifying that what sort of hyperparameters we are going to introduce, and which could be tuned. So we have introduced two set of hyperparameters, one for RBF kernel and the other for linear kernel, and we are storing it in parameter grid, and then we will pass it on into the grid search CV function, right? So that actually helps us to find out which hyperparameters. It runs the model with all the hyperparameters and tells us which is the best result. So over here, if you can see that two types of kernel, linear and RBF, is used. So data is both linearly and non-linearly separable. And if data is linearly, non-linearly separable, we don't know exactly which one will fit better. So we are using both. And in case of RBF, we have to tune C and gamma. So for C value, we are using 0.1, 1, 10, and 100. So all four will be tested. For this SVM gamma, this it controls how the influence of each data point is. So scale, there are values which we have taken as scale, which is automatically determines. Then data dependent on, we can also tune the values ourselves, like 0.01, 0.1, 1, and if large value, if it is taken as 1, that means it is going to be complex, highly local boundary, as we have discussed earlier. That is how the gamma, large gamma and small gamma, how it influences, right? So accordingly, we can see, we can put all the values and see which one is classifying better. Means having a larger margin is better, or a smaller margin is better, and all this, and the influence is larger or small. So C controls the that part, that is the width of the margin vis-a-vis how much would be the penalizing factor, and gamma controls the the influence factor, that is how much that particular point will be influencing. So that is, both of these can be tuned, and similarly we can tune the C value only in case of linear kernel. And once we have done that, what we do is we divide use the stratified k-fold function, which ensures that class proportions are preserved in every fold, and we do 5 splits, and we do 5-fold cross validation. So we have already discussed cross validation earlier. So that means we split the data into 5 parts, 4 parts used for training, 1 for validation. And then we also can, the term shuffle actually says that true randomizes data before the splitting. That means shuffle equal to true ensures that the before splitting the data is randomized. So if in case of binary classification, we can go for ROC AUC, but in case of multi-class classification, we have to go with accuracy scores. So, but in this case, it's a binary classification, so we will be able to generate the ROC AUC score. But in case it was not like that, then if it was a multi-class problem, then we could have gone for an accuracy score. So the code actually allows us to go for check both and accordingly report. So this CV stratified k-fold actually does the k-fold 5-fold validation here. And what we are doing is, again, we are checking, how many unique y values are there, and accordingly we are deciding should it be ROC score or accuracy. And then this grid search function is the one which actually help us in systematically testing that, okay, all the different hyperparameters that we have introduced, and then it finds that, okay, it tests the different SVM settings using cross validation and selects the combination of kernel C and gamma that best separates movers and non-movers according to ROC AUC. So that is what is done over here. So you can see estimated is the pipe which we have already defined, which does pre-processing as well as calls the right model. Parameter grid equal to param grid. So basically we are passing all the hyperparameters over here. Then scoring is in this case, because it is there are only two outcomes, we are going for ROC AUC. Then CV we are again doing cross validation, and then jobs equal to -1 ensures that that computer resource is the entire core is utilized, and then all the different we can fit the models, and then we can see the results. So once we have done that, we can grid.fit actually will fit the X train and Y train into the model and then generate the results, and then we print best CV results after cross validation what is the best result, and we print the best parameters. So grid.best_parameters_ prints whichever combination is the best. So we find that SVM underscore C is 1, SVM gamma is 0.01, so C value is 0.1, gamma is 0.01, kernel is RBF, and the best CV score is from the cross validation comes to around 0.988. Now, using the best estimator, this is the best model, we are now predicting X test using the best model, right? So that is happening over here, and once we do that, we can test the performance of the model based on accuracy scores, confusion matrix, and the classification report. And when we do that, we find the accuracy is 0.9365 for the test data, of course. Then this is the confusion matrix, more or less everything is perfectly classified, a little bit of mistake is there. And then this is the classification report, which shows also good division, and the total and again we are checking if it is the ROC AUC or the accuracy, and in this case, because it's a binary classification, we can print the ROC AUC score. Then what we do is, in addition to SVM, what we have done over here is we have now brought in all the other regressions. So this is a continuation of the previous program. We have now brought in logistic regression, decision tree classifier, random forest classifier, k neighbors classifier, and also the naive Bayes classifier. Now this we have not discussed. Now Gaussian naive Bayes is a probabilistic classifier which we have not discussing here. That's your assignment, that is you can actually check what it is and you can learn that on your own, and then obviously you will see that it is again another classifier which follows certain rules, certain formulations. When you understand that, you can also use that as well. It assumes feature independence and Gaussian distributions. This classifier is fast, interpretable, but less accurate when predictors are correlated. So you can also go for this Gaussian naive Bayes classifier, which is also pretty strong. So over here, logistic regression, k nearest neighbors, decision trees, random forest, all are taken just to give you. You can go through this to see if you're to just as a small reminder, and then we are setting the models first. So you see for each models we are setting the values of the hyperparameters, and for decision tree, random state 42, class weight is balanced. random forest 300 estimators, and then class weight is balanced. KNN, we are using 7 neighbors. So these are the different parameters we are passing to the models. The rest parameters are default, and then we run the model using the same pipeline that we have done earlier, but now we are changing the model to CLF, which we are over here for name CLF in model.items. So these models are passed into that, and then we can actually run each of this model and we can get the results. And so you can see over here, after we run the model, pipe underscore CLF dot predict for the test, after we train each of the models, here we are training them, CLF dot fit, and then after we train, we run the model on the test data, and we can now put the accuracy scores, right? So all the different scores that we are getting out of these models. And once we do that, then you can see that we can we will add one after another we will run the models, we will get their scores, and then we will print them, and you can see once it is printed, it comes like this. Logistic regression is 0.9683, that's the test accuracy score, and this is the ROC AUC score. And then for decision trees, this is the value you are getting. Random forest, this is the value you are getting. KNN, this is the value you are getting, and for naive Bayes, this is the value you are getting. So an SVM, already we got these two values earlier. So in this case, more or less we can see that SVM and logistic regression is performing very, very nicely. But random forest is also nearby, but ROC AUC score is pretty strong, but the accuracy result is a little bit low. So you see, which model is better depends on the data, depends on the distribution, depends on the nature of the data, number of features, number of what kind of features and so on. So sometimes it's a good idea to run multiple models and to decide which one would be best suited. So these are some of the references that we have used. To conclude, SVM balances theory, accuracy and robustness, making it a powerful classifier for complex urban data. Thank you.